Hi guys. So in the previous video, we looked at the scalar product and we did a few questions surrounding the scalar product. I did that as a bit of a revision for what we're going to be covering today. And today we're going to be covering scalar product form. So far we've looked at a vector equation form of a line. We've looked at the parametric equations of a line. We've looked at the Cartesian equations of a line. And today we're going to look at the last one, and that's the scalar product form for the equation of a line. So I've got my line in blue here, and that's just any generic line. It could be in 3 dimensions. Whatever we learn applies in 3 dimensions from 2 dimensions. And let's assume that this line has some point A. And I'm going to denote the vector, the position vector of A as a lowercase a. And that gives its point A there. We also know that any point in this blue line can be represented by the position vector r. And that r comes from the equation of the line. We know that r equals a plus lambda b, and that'll define any point on this line here. So I'm just picking a generic point r there. So a is a fixed point, but r can be any point on this line here. Now we also know that we can find the vector going from a to this point r here by doing r subtract a. So this vector r take a is traveling in the same direction as the line there, and that's an important point. Because what I'm going to introduce now is what we call the normal vector. Now, when you hear the word normal, I want you guys to think about 90 degrees or perpendicular. So the normal vector to the line is just a vector that is perpendicular to the line at any point. Okay. So as you can see, this will be our normal vector here because it makes a 90-degree angle with the direction of the line. In the previous video, we spoke about the scalar product, and if the scalar product equals 0, we know that the two vectors are perpendicular. So what does that mean? That means that if we take the dot product of our vector r take a with our normal vector, we should end up with 0 because it's given that these two are perpendicular to each other. And again, through expanding out the dot product, just like using the distributive law, we can do r dot n take away a dot n. And that gives us this result here. And we'll just move the negative a dot n to the right hand side, which gives us r dot n equals a dot n. And I've also written there that we could write this as r dot n equals c. The reason we can write it as c is because we know what the point A is. It's given. I've given you point A, and we know what the normal vector is going to be. So r dot n is going to equal a dot n, and we know that the dot product only gives us scalars. That's why it's called the scalar product and the dot product. It'll give us a scalar value, and I'm just saying that scalar value, the result of the a dot n, I'm just going to write that as the scalar e down there. So you can represent that either way. This is a really important point here because we're going to use the same ideas when it comes to planes in 3 dimensions. But for now, we'll just look at lines. And that's a really important point there, so I'd make sure that I had that written down somewhere as the scalar product form of a line, but it's also the scalar product form of a plane as well, just in 3 dimensions. So let's look at some examples now. It says find the vector equation of the line perpendicular to 5i take j that also passes through the point A to 3. And they want us to find it in scalar product form and in Cartesian form. I'm just going to draw a picture with vectors. Always make sure you're just drawing a picture to get an idea of what's happening. What's happening is we want to find the blue line. Let's get my blue line out. So we want to find the equation of the blue line. They've told us the point on the line. So the point A is over there. And they've also been really nice. And they've actually told us what the perpendicular line is going to be. Okay. Because we want to find the vector equation of the line perpendicular to 5i take away j. So that's our normal vector there. All we need to do now is we just need to put that into our equation of r dot n equals a dot n. Now r, we don't know what r is yet because r is just any point on this line here. Okay, so r is any point on the line. It's a generic point. We can leave r the same. Now our n value there is 5 minus j, and because they've written it in component form, as much as I like to write things in column vector form or row vector form, we have to write it back into component form. So 5i take away j equals, and we have to find the dot product of point A with n. So point A is 2, 3. That's the position vector of point A. And the normal vector is 5, negative 1. Now, the reason why I'm writing this one in vector form here is because I know it's going to be a scalar at the end of the day, so I don't need to worry about it being in my final solution. So r dot 5i take away j equals 2 times 5 is 10, 3 times negative 1 is negative 3, 10 take away 3 is 7. So this is our r dot n equals a dot n, and this is the scalar product form of that line that is perpendicular to this line here, and it also goes through the point 2, 3. That was part A. Now we need to talk about the Cartesian form. Once you've got the scalar product form, it's actually really easy to find the Cartesian form. Because what do we know about r? R is any point on the line with an x coordinate and a y coordinate. So instead of writing r dot 5a take j equals 7, we can just write this as our r value is xi plus y in the j direction dot 5i take j equals 7. Now we're going to multiply the components together. Now remember, we don't need to put the r's at the end of this because when you're finding the dot product, it's going to be a scalar. So we just multiply the components together. So the r components multiplied together give me a 5x, and the y components multiplied together give me a negative y equals 7. So if we know the scalar product form, just by writing our vector r in terms of x, y, or x, y, and z if it's in 3 dimensions, when we find the dot product of r and n, that actually gives us the Cartesian equation, which can be easier than converting straight from the vector equation to the Cartesian equation. Next question is going to be determine if the points below lie on this line. Okay, now we know that for points to lie on a line, they must satisfy that r dot n equals some constant c. All right, and we're going to be substituting in these values for r. For the first one, I'm just going to write these as vectors now. We'll do a first. So the point that we're going to try first on the line, because remember r is any point on the line, so we're going to substitute in these points on the line, is 0, 6. And we're going to find the dot product with that and 1 and 2, because that's the normal vector to the line. And when we find that, 0 times 1 is 0, plus 6 times 2 is 12. Now, because that's the same as this 12 here, the point A does lie on the line, because it does satisfy this equation that r dot n equals 12. Let's try point B now. So point B is negative 4, 8. Again, I'm substituting that in as my r position vector. And again, the normal vector to the line hasn't changed. It's still 1, 2. And when we solve this, we're going to get minus 4. Because negative 4 times 1 is negative 4. And 8 times 2 is a positive 16. And that also equals 12. That also satisfies this equation here. Therefore, the point B also lies on the line. Let's try the last point now. We've got 3 and 6. And again, we're going to take that with the dot product of 1 and 2. 3 times 1 is 3. 6 times 2 is 12. 3 and 12 is 15. And that does not equal 12. Okay, now because this point, 3, 6, does not satisfy this equation here, it does not lie on the line because it didn't equal 12. All right, last question now. Prove that the lines are with this equation and are with this equation are parallel. I'm just going to draw a line quickly. Let's just draw a picture. Okay, so if this is the first equation, we know that the direction of this line is 1, negative 4. Okay, we know that this line is traveling in this direction. Here, I could also go backwards, but that's the direction of the line. In this form here, what they've actually given us is that this 8i plus 2j, this is in scalar product form. So again, that's r dot n equals a dot n, which equals c. Okay, so this 8, 2 is actually the normal vector, 8, 2. So if these two lines are parallel, we know that the dot product between the normal vector and the direction of the line should equal 0. Now, if it equals 0, then that means that 8 and 2 is also the normal vector of our first line. And that means that if this is the second line here, they both share the same normal vector. Okay? If they don't share the same normal vector, they are not parallel lines because there's only one normal vector for each line. So let's go ahead and test that now. Let's test if this direction of this line is in fact normal to this line here. And we know that when two lines are perpendicular to each other, we know that their dot products should equal 0. So this is the direction of the line, this is the normal vector, and if it equals 0, then the two lines will be parallel because they share the same normal vector there. So 1 times 8 is 8, negative 4 times 2 is negative 8. This does equal 0. Now, because it does equal 0, that means that the first line and the second line are parallel because they share the same normal vector there.